In 1859, Bernhard Riemann proposed a conjecture linking the discrete distribution of prime numbers to the continuous flow of a complex function. Over 160 years later, this remains the most enduring unsolved problem in mathematics. This is the foundational textbook map of the Riemann zeta function in the complex plane. You can see the trivial zeros marked exactly along the negative even integers on the left side of the axis, but the unsolved mystery lies entirely within this vertical region. This is the critical strip, bounding every complex input where the real part falls strictly between 0 and 1. The Riemann hypothesis imposes a rigid constraint on this space. It asserts that every single non-trivial zero of the zeta function must fall exactly on this one-dimensional center line, where the real part is precisely 1/2. When we compute the first roots, they land directly on this coordinate. We find non-trivial zeros exactly at 14.13i, 21.02i, and continuing upward. Over the past few decades, mathematicians like Andrew Odlyzko have verified this empirically. We have now computed the locations of the first 10 trillion consecutive zeros. Every single one sits exactly on this line. In the domain of continuous mathematics, 10 trillion examples do not equal a proof. The sequence extends infinitely, meaning empirical verification can never mathematically guarantee that the next zero will not deviate. This absolute requirement for analytical certainty introduces the first structural barrier, the one codimension trap. A common analytical strategy is to attempt to prove the hypothesis by progressively narrowing the boundaries of the zero-free regions. You calculate boundaries on both sides of the critical strip and slowly squeeze them inward. The math makes this strategy impossible. Shrinking a two-dimensional boundary asymptotically toward a one-dimensional target is an infinite sequence. You can slice the distance in half forever without ever closing the gap. Any valid proof must bypass this infinite loop entirely. It requires a mathematical mechanism that natively detects the 1/2 line itself, distinguishing it from the surrounding plane at step 1. Because of this codimension barrier, the solution cannot come from squeezing the zeros from the outside in. The alignment must be generated algebraically from the inside out. In the early 20th century, David Hilbert and George Polya proposed a theoretical blueprint that satisfies this exact requirement. They suggested that the imaginary parts of the zeros act as the eigenvalues of a self-adjoint operator on a Hilbert space. If such an operator exists, the spectral theorem guarantees its eigenvalues are strictly real, locking the zeros permanently onto the critical line. This remained a highly abstract idea until 1973, sparked by a chance conversation between number theorist Hugh Montgomery and physicist Freeman Dyson at Princeton. Montgomery was studying the Montgomery-Odlyzko law, which mathematically maps the local statistical distribution of the spacing between the zeta zeros. Dyson recognized Montgomery's formula immediately. It was the exact distribution describing energy levels of heavy atomic nuclei, specifically eigenvalue spacing in large random Hermitian matrices, the Gaussian unitary ensemble. The statistical distribution of prime zero gaps perfectly matches quantum energy levels. This multi-decimal precision provides overwhelming structural evidence that the Hilbert-Polya operator physically exists, even if we cannot actually isolate it. In 1999, physicists Michael Berry and Jonathan Keating proposed a highly specific candidate for this missing operator, drawing from the mechanics of quantum chaos. They introduced the Berry-Keating Hamiltonian. Here, x represents position and p represents momentum, with the symmetritized product accounting for the fact that position and momentum do not commute in a quantized system. The construction is elegant, but it harbors a fatal mathematical flaw. The operator as written is not natively self-adjoint on standard mathematical spaces. Making it self-adjoint requires specific boundary conditions, but enforcing the exact conditions needed to align the spectrum implicitly assumes the Riemann hypothesis is already true. The Berry-Keating approach relies on circular logic. It translates the Riemann hypothesis into quantum mechanics, but lacks the internal machinery to independently prove it. Looking beyond physics, Alain Connes attempted mapping the primes using rigorous tools of non-commutative geometry. He built his framework on the Adel class space, a topological staging ground that unifies standard real numbers with all possible completions of the rational numbers. Within this space, Cons constructed a dilation generator flow, where resulting geometric periodic orbits correspond directly to prime numbers. To lock the spectrum onto the critical line, his geometry relies on a trace formula, requiring a specific positivity statement to hold true. When André Weil solved the equivalent hypothesis for function fields decades earlier, his proof worked precisely because finite fields natively possess a proven geometric positivity. The integers do not. Without native geometric positivity for the integers, Kans's framework is a brilliant mathematical translation that stalls exactly at the finish line. Recognizing the extreme difficulty of supplying this missing geometry, some mathematicians bypass physics and topology entirely in favor of purely arithmetic equivalencies. This is the Kuiper-Lee criterion. Looking at equation 1.3, it translates the Riemann hypothesis into a requirement that a specific real number sequence remains non-negative. Prove these coefficients never drop below 0 as n scales to infinity, and the hypothesis is confirmed. But evaluating this equation collides directly with the limits of algorithmic complexity governed by Chaitin's theory. Verifying this sequence requires extensive integer factorization. The computational cost scales exponentially as inputs grow, permanently trapping generalized verification outside the reach of polynomial time calculation. Arithmetic criteria present a mirage of simplicity. They hit an absolute computational wall, demonstrating the Riemann hypothesis cannot be brute-forced without deeper analytical invention. When we pull back and map these disparate fields of attack across the critical strip, a unified pattern of failure emerges. We require a self-adjoint operator. We require trace positivity. And we require a mechanism for native one-dimensional detection. Quantum physics, non-commutative geometry, and arithmetic equivalency all stall at the exact same logical gap. Modern mathematics currently lacks a native mechanism to guarantee geometric positivity over the discrete integers. Refining existing bounds, running larger supercomputers, or narrowing zero-free regions will never bridge the gap between the discrete primes and the continuous plane. A definitive solution will only emerge when we invent an entirely new arithmetic geometry, one that inherently possesses this positivity at its structural foundation. The Riemann hypothesis remains unproven, not because it is false, but because the architectural framework required to see its truth has not yet been invented.